From our phones to our cars and even our power grids, our whole world basically runs on these super powerful lithium-ion batteries. They're these little marvels of engineering, right? Packing a ton of power into really tiny spaces. But what happens when all that power gets unleashed in, well, the wrong way? Let's dive in and find out.
Yeah, when you look at an EV battery, it's not just one big block. It's actually this complex, interconnected system. We're talking hundreds, sometimes even thousands of individual cells all working together in harmony. Now, failures are incredibly rare, let's be clear. But with that much energy crammed in there, the consequences can be, well, pretty severe.
And that right there, that quote, it really gets to the heart of the problem. See, it's not about just one single cell failing on its own. It's about this dangerous chain reaction, this domino effect that scientists call thermal runaway. One bad cell can literally take the whole pack with it, and that is the nightmare scenario everyone is trying to prevent.
So what's actually happening inside one of these battery cells during an event like this? On a chemical and physical level? Let's break down the science behind this incredibly fast chain reaction.
Right, so thermal runaway isn't just one big boom. It's actually a super fast three-stage process. As you can see in this graphic, a tiny internal problem can escalate into a massive one in like the blink of an eye. It releases all of that cell's stored energy almost instantly. Okay, so it all kicks off with overheating, stage 1. This could be from anything really, a car crash, an electrical short, even a tiny manufacturing defect. Now, this heat starts to melt something called the separator. It's just this thin plastic film that keeps the important bits apart. Once that's gone, things escalate and they escalate fast. The internal components start to break down and they release all these flammable gases. That's stage 2. And finally, you've got heat, you've got fuel, and you've got oxygen, and you get stage 3, combustion, fire. So you see, the real key here isn't just preventing that first failure. It's stopping the chain reaction. It's about preventing those dominoes from falling. And that is a seriously complex challenge that pulls in chemistry, material science, and some really, really clever engineering.
And believe it or not, it can all come down to this one number, 150 degrees Celsius. In a recent 2024 study, researchers pinpointed this as the critical tipping point. It's the exact temperature a neighboring cell has to reach for the failure to jump from one to the next. I mean, knowing that specific number, that's a total game changer for designing safer systems.
Okay, these X-ray images are just fascinating. On the left, you see what happens when a nail is punched through a cell. It's this violent, localized explosion in that first trigger cell. But look at the image on the right. That's the second cell, the one that fails just from the heat of the first one. It behaves totally differently. It's more of a slow burn, with the failure spreading all the way through. Understanding these two different behaviors is absolutely crucial for building safer batteries.
And it turns out even simple design choices can make a huge difference. For example, if you wire the cells in series, a failure gets way hotter. But if you wire them in parallel, a healthy cell can actually dump all its current into the failed one, which is also really dangerous. So with all these variables, from wiring to chemistry, how on earth do you guarantee safety across the board? Well, you need a standard, a rule book.
Right. So when they're faced with all this complexity, engineers don't just guess. They follow a rigorous, data-driven rule book that's designed to make these batteries as safe as humanly possible.
So yeah, this is the multi-billion-dollar question, isn't it? How do you predict and prevent a dangerous domino effect that happens in milliseconds? Well, the answer is surprisingly straightforward. You test. You test rigorously, and you test repeatedly.
And the industry's answer is this series of absolutely brutal stress tests known as UL 9404A. Think of it as the official rule book for battery safety. It's actually required by fire and electrical codes, and its whole purpose is to push batteries to their absolute limits, to understand exactly how, and more importantly, when they fail. And the results from all this testing are incredibly practical. I mean, this data informs everything, from how far apart battery systems should be installed, to what kind of ventilation they need, all the way to providing crucial life-saving information for firefighters on how to actually handle an emergency. This is real-world impact. Okay, so let's go inside the lab for a minute and see how this standard actually works. How do these scientists and engineers put batteries through their paces to make sure we're all safe? So UL 9540A uses what's called a graduated approach. You start small, right at the single cell level. If it passes that test, you might be done. But if not, you have to move up. You test a full module of cells, then a whole unit, and sometimes you have to test the entire final installation. It's a system that's designed to build safety in at every single level from the ground up.
And it all starts right here, with just one single cell inside this specialized pressure vessel. In this super-controlled environment, engineers will intentionally trigger a failure, and they'll use everything from heaters to, get this, nail guns, just to see precisely what happens.
Now, when a battery fails, it vents this mix of gases. This machine here, a gas chromatographer, it basically acts like a high-tech sniffer. It analyzes that gas to see exactly what's flammable and what's toxic. And that information is absolutely vital for creating effective early warning systems.
Next up, they need to know how fast a potential fire could spread. So what they do is they create a synthetic replica of the gas that was vented. And then they use these crazy high-speed cameras to measure its burning velocity with incredible precision. And that data, it directly influences how they design fire barriers and how much space they need to leave between battery modules.
So let's just tie this all together, right? The pressure vessel, that measures the force of the failure, which helps design stronger casings. The gas chromatographer, it identifies the fuel, which helps create fire suppression systems. And the high-speed camera, it measures the speed of the fire, which helps design effective barriers. See? Every single piece of data has a direct safety benefit.
So all this controlled destruction in the lab, it has a very, very constructive purpose, building a safer, more reliable energy future for all of us.
At the end of the day, this is how progress is really made. The fear of a rare, but, dangerous event is replaced by understanding. And it's through that understanding, through data, through analysis, and through rigorous engineering, that we build safety directly into the technology that is literally powering our transition to a cleaner future.
But the work is never really done, is it? As engineers keep pushing the boundaries, creating batteries that are even more powerful, even more energy dense, the challenges are just going to evolve. So the question we're left with is, what's next? What new materials, what new designs, and what new testing methods will be required to keep us safe in the decade to come?